Let's kick the day off with a little presentation about where we're at in the industry in general, right? So we're going to be talking about GFRP today, but I'm representing ACI 360, the Slab Design Committee, and the remarks that I have will be general in nature, whether it's GFRP, fibers, traditional rebar, or plain concrete. So the idea, I think Celeste really set the stage very well. I hope that you leave today with ideas. We are creators, we're thinkers. I think most people in the room, just looking around, except for the young ladies, the gentlemen, there's a few gray hairs in the room that are going to have been around for a long time, and the ladies are very knowledgeable too, don't get me wrong, but just think of this presentation of mine at least as ideas, right? As we all come together in a new and dynamic world, okay? I am Jim Loper out of Arlington, Virginia. I'm really happy to be with you today. Here's an agenda for the next 30 minutes or so. I love to start with the why. We have a very dynamic industry right now, right, Celeste? Yeah. I'll give you a little update from ACI 360, right? Talk about some references. And then from a two-day seminar that we gave last year, I boiled it down to just 5 things that may be interesting to this group. And if you'll close that door, it may help a little bit. Okay, after the opening ceremonies last night, I had a couple of really interesting conversations. One gentleman came rushing up to me and he said, Jim, we've got big trouble. We're grinding slabs left and right. The market is changing so fast that at least one big company that you would know if I said their name, they have robots working on the slabs 24/7, carrying very heavy items, and the wheels are tearing up the slab. And yep, okay, that's fair. And also on top of that, what this particular group had done was to buy a fleet of buildings and try to adapt them for their needs, which really isn't working out in the long term, but they were trying to adapt to what was already there, right? And so now we're working back through some of that. You couple that with the notion that what are the 2 most important cost drivers for an owner, in a typical warehouse? The roof and the floor slab, right? That's where most of the money goes in a life cycle. That's what folks are thinking about. Then you toss in the new crushed limestone mix, the type 1L. I think probably most of you have encountered it by now. We're taking crushed limestone and replacing some percentage of the cement. So that's going to change the characteristics a little bit. Then you bring in the new technologies with GFRP, fibers, admixtures are always changing. And then on top of that, you go to the grocery store. If you're like me, you pay $10 for an egg. It's a lot of money, right? So materials and labor. We just talked, Celeste introduced the notion that GFRP is lighter, it's faster to install. If we can get the same value faster and with less cost, why wouldn't we do that, right? That's part of why we're here, adapting to changing conditions. And then I told a little story about fulfillment, right? This particular owner has very tall storage racks. Sometimes they have narrow aisles. They have the robots that are working 24/7. They have speed machines that are going back and forth with really small wheels. They have folks that are dragging pallets and pushing pallets right across the floor to just try to get from one end to the other. So many things are happening in the market. Geotechnical concerns. We've got soils that will sometimes heave, right? Just all sorts of things happening right now. All right, let's take a breath. Think about what ACI 360 has to offer. It's mainly 4 types of slabs that we address. Think of a plain vanilla 6-inch thick slab, no reinforcement, or cut the joints. It's generally going to be happy until we start putting loads across the joints. It's hard to break a slab except at the joints, at least in my experience. Another one that's talked about in ACI 360 is slabs that are lightly reinforced, call it 0.1%. We talk about that in the document, but we don't talk about it enough. There's going to be a whole new chapter on that coming up. Another way to approach it is to extend the joints to where we call it a jointless floor slab. and really load that one up with about 0.5% steel or more, that's a lot of rebar, very costly. A third way to approach it is to take a more proactive approach. And I think that the shrinkage compensating concrete has come a long way. I think it's really viable these days. I think it's a great option to be proposing to actively try to control shrinkage. Post-tensioning would be another good way where we actually introduce a compressive stress before the slab ever gets loaded, right? And then the hot topic, oh boy, I'm just the messenger here, folks. On number 4, there's a lot of discussion in ACI 360 and various circles across the country about what constitutes a structural slab-on-ground. And so the really smart people in the group are still debating that right now, if we put a new mezzanine on it, if we put people up on a platform or on a storage rack that has people up there. To me, that is a structure, and if it's setting on the slab, personally, I think that the slab should be checked for factored loads, but there is some debate and some gray areas there, right? That particular document, 360, hasn't been updated since 2010. We're in the process. We've revised most of the chapters. Those are being adjudicated and voted on right now. I expect within the next year or so it'll go to TAC. Then we'll be hammered with those comments and so forth, but we will get there eventually. One of the hot topics in ACI 360 right now is right out of IBC 2024, there's a couple of new provisions in there, 1907.1 and 2, that talks about what's structural and what's not structural. There were a flurry of emails and phone calls just last week as we prepared for this meeting about what constitutes structural versus non-structural. The other one that we'll do a little bit more on is extended joints. Right now, the sweet spot is either jointing the slab regularly at about 12, 15, 16 feet on center, or going jointless. There's a portion of the market that would like to see intermediate joints, and we're trying to address that in the document. All right, here's the flow down. Here's where we start. Typically start with IBC that flows down to ASCE 7 and ACI 318. Those are the golden books, right? Everybody's going to follow that. The reminder here is that ACI 302 and 360 are recommendations. Those are guide documents. I can't just refer to them as code, right? If I want something in my contract documents that's in those two, I have to pull it out and put it in my specs or drawings so that it's enforceable, right? Also keep in mind that 302 is a construction-related document. 360 is a design-related document. They go hand in hand. I suggest that folks have both of them in their library. The third one I have here is TR34 out of Europe. It's a European-based recommendation document and has lots of good examples in it on how things are done in the European market and other places. I think it's a terrific document as well to have in your library. All right? Okay, so 5 things, just 5 things out of a 2-day seminar. True story. Last night, after their session, another fellow comes running up to me. Jim, I've got a heaving slab. Well, what happened? There was a rain event sometime before a slab was placed, and the soil was known to be prone to shrink and swell. Well, for whatever reason, they went ahead and cast the slab, and before they could cut the saw cut joints, it was a little cold, so they had to wait so they don't ravel the saw cut joints. Before they could start cutting, the slab was cracking because of heaving, right? So the point here is that we've got to engage the geotechnical engineer early and often. We need to understand the soil conditions so that we don't get cases like this. We want to be within about 3% of the optimum moisture density. And here's what we want. I showed you the bad. It looks sort of like a gunslinger movie with, show you the good. Typically speaking, we'd love to see a road-based material that's about 4 inches thick, it's compactable, it's trimmable, it's not beach sand, it won't rut or pump with a fully loaded mixed truck or dump truck. Here again, this plays out regardless of whether it's GFRP bars, fiber slabs, or unreinforced slabs. Trimmable and compactable, something we can work with. Here's why that's important. This is not Photoshop. This is an actual photo at the bottom left of a slab that was designed to be 6 or 7 inches thick. And in some cases, it was as thin as 3 inches thick. Now, granted, maybe those were localized areas, but it is concerning that when we look at what tolerances should be, we would hope for a little bit better than that. And the reason for some of that is contributed to the subbase, the base preparation. The good news these days is that most contractors have access to laser-guided vehicles. They can trim the base. So I'm just showing you some extreme examples, but we want to be really careful about setting up the ground, right? Number 2, mix design. We were just talking about that earlier today. We've got a number of people that I've already met just walking around the halls. I was on the elevator this morning, and this lady's coming down with me, and she saw my brochure, and she says, "Oh, are you with ACI?" "Yeah, I'm with ACI. I'm out of St. Paul." I said, "Well, nice to meet you." And she's definitely into the material science part of it. So we had a lot to talk about, and she rode all the way down with me. She was going to the gym, but she says, no, I'm going to go to the lobby and talk with you about aggregates. I want to know what you think about mix design. And so I basically went to practice my slide with her to think about packing as much coarse aggregate, middle-size aggregate, and fine aggregate into a volume of mix as we possibly can to minimize the paste. Why do we minimize the paste? Because typically speaking, the paste is what's going to contribute the most to shrinkage and ultimately to cracking. So if we can optimize the mix design with a workable water-cement ratio, normally around 0.5, maybe some of you will debate that, but sometimes I see mix designs that are 0.35, 0.4, 0.45 without an apparent reason. Well, what does that do? It just forces the ready mixer to put more cement in. So if we can go with something that's reasonable and get a good placeable, pumpable, finishable slab, then 9 times out of 10, if we do our other homework, we put our joints, we know our loads, we're in good shape. Keep in mind that it takes about 2 seasons or 2 cycles for most all the shrinkage to come out of a floor slab. Once we turn on the air conditioning or the heat, whatever it might be, if we do have cracks, we can go ahead and fix those in the first season, but there will be some that need to be fixed in the second season. So it takes about 2 cycles typically. All right? And here's what that might look like. Here again, last night I was talking with somebody who was talking about slivered aggregates versus round or angular. All of those things come into play, and that's where our friends in the ready-mix industry can tell us a lot. That's one of the first calls I make. When I have a new project, whether it's in St. Paul or Atlanta or Irvine, California, wherever it might be, is to find out who are those professionals that are actually working with that mix design every day. Some of you may work in local markets. My practice is nationwide, and I need to be communicating with the contractors and the ready mixers as quickly as possible. All right, I don't always have this option, at least in my practice. Folks want to get on the slab quickly. I've only had 1 or 2 in the years that I've been designing where I could keep loads off the slab to 56 and 90 days. But keep in mind that if we're using particularly higher dosages of slag or fly ash, those types of things, we may not hit our 28-day strength, our F'(C) value, until 60 or 90 days. And that we did some predictions ahead of time on this big 5-foot thick wall that we were designing, and it hit with 50% fly ash. It hit the F'(C) value exactly at 90 days. I was really happy about that. And we had the luxury, we didn't have to load that structure up until later on because some other things had to get built. But just keep that in mind, right? Okay. I'm talking really fast, so I'm going to slow down, right?
You're good. You're good.
Doing good?
You have plenty of time.
Oh, I know I have plenty of time. I'm not sure I have plenty of material. So we can kind of take our time a little bit. As designers, as practitioners, as contractors, what does ACI 302 and 360 have to offer? Regardless of whether it has GFRP bars or not, I'm suggesting that we study the graphs and the tools that are available. Show of hands, has anybody used these charts before? Don't be shy, right? Okay, so we got a good showing. Some have, some haven't. But the take-home message here, without going into all the details, is that there are tools available. If you call your local ready mixer, if you can get the submittal for how much cement, the gradation for the aggregates, you can run your own little spreadsheet. I've got mine, maybe you all do too. I see a smile here, I've got a couple of smiles going on. Yeah, we can run those fairly rapidly. Within just 30 minutes after you receive the submittal, you can type all the information in and plot these charts out, right? And look at what's called the haystack curve or the tarantula curve, and then decide for yourselves, should we try to change the blend, or is it good enough with what we have in a local market? Here again, Jerry Holland is quick to say, Jim, you get what you get, don't pitch a fit. And so in Atlanta, Georgia, you're going to get granite, right? And up by me in Virginia, you're going to get limestone. One of the good, really helpful charts that I've used a lot over the years is in the lower left-hand corner, the coarseness factor chart. Sometimes we have gap-graded aggregates. Sometimes they're too bony, sometimes we're too fine. The yellow is what we're calling the optimum. This chart was created by Shieldstone many years ago, for those that may not have seen it. But if we can get close to that yellow trapezoid, we're generally in pretty good shape with our mix design. Now, one of the best concrete contractors in the country, he comes running up to me one day, and he says, Jim, I just can't get to that yellow target. I'm just outside of it. I said, Scott, you've done all of these other things correctly. You've detailed it. You've got the rebar. You've got the dowels. You've got the joints laid out. You got a lot of things going for you. If you're right there at it with locally available materials, you've done the best you can do, right? Sometimes I meet people that are like, oh, we've got to be in that yellow target, right? There are exceptions, okay? There's exceptions to every rule, all right? So let's just remember that, all right? Okay, fibers. We were talking about fibers earlier today, right? In pavements, the macro-synthetic are popular. In my experience, I've used both the macro and the steel fibers, not so much for the micro. Those can be blended together. I think there's no reason that they couldn't be used in combination with GFRP. You know, it's another consideration, another cost factor, right? But those are fairly mature in the market. They enhance various properties. We've used them in conjunction with rebar over the years. We've gotten into a lot of unusual situations. For example, I was designing an industrial dryer many years ago where we put in silica fume and steel fibers and reinforcing and early age concrete because we wanted to come back after an offline situation very quickly. So you may find yourself in cases where you need to combine various materials, all right? And just one example, not to promote one type of fiber or another, but these, we can deliver, you know, beautiful, long-lasting, durable floors with these types of fibers. This particular example is 8 inches thick with 33 pounds per cubic yard of hook fibers. In my experience, somewhere between 30 and 60 pounds per cubic yard of steel fibers is what I typically have seen. And with the macro fibers, maybe a pound or 2 pounds per cubic yard, something like that would be our target. Okay, here's another funny. We were talking just this morning. Here's a joint layout, right? This particular one is a perfect condition of a rectangular footprint on the building. And we're going to cut joints and tell that slab, I want you to crack right here at these different locations. If I've got lift truck traffic, I'm going to provide some sort of stability probably across the joints there. But the problem is, at least in my experience, I'll have an elevator over here, I'll have a ramp here, I'll have a loading dock up there, and suddenly my slab will be chopped up, right? And so what I spend a lot of time thinking about the joint layout. And I have some folks, some colleagues that just sort of leave it up to the contractor. We were just talking about that this morning, that if you leave it to the end, and it's 90 degrees out there on a Friday, and they're getting ready to cut the joints, what are you going to get? But if you plan ahead with your best ideas of how to do the joints, you're going to get what you asked for rather than the opposite. Does that make sense? So I'm suggesting to go ahead and plan the joints. And joint stability is, in my view, it may be the number one thing that we deal with right now. All right? Let that settle in for a minute. That's debatable. But it's got to be in the top 5, right? Joint stability. I see a lot of heads nodding. Okay. How do we reinforce the joints? We can run rebar through the joints continuously, or we can put dowels. I didn't show the round dowels. The plate dowels are popular in the industry, both at saw cut joints and at construction joints. The warning there that we talked about just this morning is that the dowels do need to have the adequate cover. Got to be careful about that. We don't want the dowel baskets to be displaced during the concrete placements. The rebars, or whether it be GFRP or steel bars, typically don't have that negative influence. Negative is a tough word, but we just have to be careful if we're going to use dowel baskets that they remain in place during the placement of the concrete, all right? And the message here is that there is some guidance in ACI 360 about the spacing. The dowel manufacturers can help with the size and spacing depending on the loads that you have, all right? Okay, now this is one of my favorite charts. I use this one quite a bit, right? On the left-hand side, it's an easy-peasy chart. We have on the x-axis the slab thickness, the joint distances are on the y-axis. So then we have different levers that we can use to control what's happening with our slab. If we feel like we've got a slab that's going to shrink a good bit, that's got a higher shrinkage potential, we can dial down the joint distance, right? So for example, if we had an 8-inch thick slab, if we think we've got just typical concrete, what does that come out to be? About 16, 17, 18 feet on center. If we're a high shrinkage potential, then we may back it off to about 15 feet on center. The balance there, the balance is the more joints we put in, the more maintenance we have on those, right? So you have to think for yourself as to what you believe to be a reasonable joint spacing for whatever shrinkage you think you may have. And hopefully the concrete supplier or contractor can provide shrinkage results testing to tell us whether it's going to what we would consider low, medium, or high shrinkage. For most of my projects, I don't typically have the testing up front because I work in a design bid build atmosphere typically where the contractor isn't known until after the drawings go out. And I'll typically assume a typical concrete. I'll usually use the green line for my layouts. I think that's fairly reasonable. And if you do all the other things, all the other detailing, the reinforcing, the dowels, the curing, then you'll typically be in good shape. Oh boy. Okay, here we are. We're on number 4. Number 4, talking about wheel loads and all sorts of other loads. To me, this is a big deal, right? Joints. We talked about joints a good bit already, but joints are in my view, the leading cause of headaches for owners. And it's these small wheels. It's a case where we also have the robotics where things are being drug across the floor. Even if there's just a little bit of play in the joint, it'll start wearing on it. All right, other loads to consider. Now, here's one. Remember we talked about a hot topic in ACI 360 about what constitutes structural concrete? I think most people would agree if you have a pre-engineered building with thrust forces, reactions at the base from the pre-engineered building columns, we typically would put in hairpin bars in the slab to keep it from thrusting, right? That's a factored load combination to where the hairpin bars and the amount of concrete you need to hold it down would be in accordance with ACI 318. In my practice, on the lower corner picture there, we're being asked more and more to retrofit slabs with mezzanines. Adaptability. Remember we talked about it on the first slide. And what constitutes structural versus non-structural concrete. I'm going to call that a structural slab because there's people working up there. And I'm typically going to try to make those base plates big enough to where I don't punch through the floor or I don't have a flexural problem. Punching shear typically doesn't control, but it's a really hot topic right now. And just the thumbnail for a new slab, if we put fibers in it, can we count on the fibers for punching shear resistance? And so that's a hot topic right now. The other one to keep in mind, we have taller and taller storage racks. It's important to couple or connect the two middle columns so that we get a much larger lever on, right, for overturning, and try to minimize the amount of uplift there. Another consideration is when we have uplift and the slab is actually in tension, oh, that seems like a structural consideration. That here again, we're debating that in committee right now. Okay, number 5. This is the last big thing to consider, right? We're still doing good on time, plenty of time, right? And it's the last one. I promised Richie to give an overview of historic approaches to thickness design. And I put this at the last on purpose. You know why I did that? I put it last because if you've done all these other things, you know your loads, you know your soils, you know what you're going to do for curing, you know a bunch of different things. You know you're going to put dowels. It'll take me typically about an hour or less to come up with a thickness. That should be, in my view, one of the quickest things that goes. And the reason I say that is there's so much literature available. In ACI 302 and 360, there's a number of graphs, monographs. If you know your loads, if you know your K value, if you know your F prime C value, if you know what factor of safety you want to use, then it falls out pretty quickly, right? All right, Westergaard. It all started with him in the 1920s and 40s. Elastic-based theory. Think of your bed springs at home. You're laying on your bed, and there's springs down below. That's how we're modeling the soil, right? It's actually a continuum. We all know that, but we're going to model it using springs, and most of the time, that works pretty good. Then Meyerhoff comes along in the 1960s, and he improves it a little bit. And what he did was to introduce the yield line theory, which is it's really a step in advancement from what Westergaard was talking about. And for a concentrated load, I'll show you a picture here in a minute, what we do is allow the slab to crack at the bottom. Nobody really cares about cracks at the bottom. We're going to radiate the slab that cracks up to the top. We'll have a circumferential crack at the top. We'll back that off so that we don't see the crack. We don't actually have the crack up there, right? And I'll show you a picture of what that looks like. Shinto. We get that question a good bit. A fellow by the name of Shinto developed yet another model. And this one really is an ultimate strength approach where for a concentrated load, we're cracking the floor. At that point, the slab is behaving independently like a footing. Think of a circular footing with a concentrated load, circular footing, and it's independent of the slab. Now that really is an ultimate condition, right? And then the last thing is finite element modeling. I've done my fair share of finite element modeling. It has the power is that once you get the model built, you can run a whole bunch of different scenarios rapidly, right? It's all about the assumptions, the boundary conditions, and getting those right and feeling comfortable with that in order to have a reasonable result. All right, picture worth 1,000 words. We talked about bed springs, right? The concept is that the springs are decoupled. They're not working together. They are not a continuum like we know the soil really is. But in a lot of cases, it gives a reasonably conservative result that is within some range of what you could do with Westergaard or with Meyerhoff and some of the others. You can sharpen the pencil and go on from there. But this is a pretty good place to start. And here again, there's a whole bunch of guides within ACI 360, tables, monographs, that can help you get to a thickness fairly quickly. All right, our friend Meyerhoff, right? He comes online in the 1960s. We're letting the slab crack at the bottom. We're going to radiate the cracks up to the top. We get a circular crack at the top. Now here's where the reinforcing and the fibers really come into play, right? If we have the right amount of reinforcing, the right amount of fibers, then Meyerhoff's approach makes a lot of sense. right? Let that soak in for just a minute. And over on the green part is where I'm suggesting that we back it off by some safety factor or some means to keep it from cracking at the top. We don't want to crack here at the top, right? All right, and then for the Shin-2 method, here again, I'm just cautioning, that has been published. It's in an older version of maybe Concrete Construction Magazine or so. It's going to show, for the same types of concentrated loads, a very high ultimate strength, whereas maybe you'll get 10 kips out of Meyerhoff. This might show 30 or 40 kips of capacity using the Shin-2 method. In order to achieve that, we're going to have fairly large displacements. There's nothing wrong with research that was done overseas, but in this case, it wasn't, I don't think the research was vetted by university professors or folks that are really in the know on this sort of thing. It was also based on 1 and 2 inch thick slab thicknesses and then scaled up for 6 inches and more. So I'm really just cautioning people about using the Shin-2 method, all right? And then lastly, just to show a few pictures of what the finite element method looks like. I like it once we get it set up, and if we get our boundary conditions and our material properties correct and reasonable, then we can model a lot of things. We can model the soil as a continuum, and most of the time, the depth of influence will only be 14 or 15 feet. We can model uplift, we can model compression-only springs, we can model nonlinear material behavior if you want to go that far. I've done it, but I wouldn't recommend it for those, if you're doing this at home, right? I'm getting some smiles here, right? You don't want to go there unless you have to, right? And if you've got complicated loads, if you've got stepwise loads, if you've got, I don't know, progressive collapse, whatever, I'm just throwing some things out. If you want to know more about the soil, how it's going to behave, could be a good option. But it's probably going to take significantly more time to do, to set the thing up, to get it right, to get comfortable with it. But once you do have the model.
Which software is this?
I'm sorry?
Which software is this?
Oh, right. The software is a good question. Thanks for asking that question. The lady asked what software is available. I myself have used SAP a good bit, and it has the continuum or brick or 8 noded elements in it. SAP, ETABS, RISA, STAD. I think most all of them have that these days. So I won't be a proponent of one or the other, but it depends on perhaps how you grew up. I grew up with STAD, but then I learned SAP a few years ago as well. So those are my favorites. And it seems like every engineer in our office has their favorites, right? And then I go to other Jacobs offices, and those people have their favorites. So it varies even within my company. I'm getting another smile there, so I'm sure others are encountering this. That's a great question. Thank you for that. And lastly, all right, Tony, I think you're friends with Jerry Holland. You've got to be friends with Jerry Holland.
Yes.
I was 20-some-odd years old at Lockwood Green many years ago, and I was designing beams, columns, slabs, braces for Jerry and Wayne, and I would get it down to the gnat's tail. I had nailed it. ACI 318, AISC, I had my beams, my columns, everything was all set up. Well, the next day I would come in, and Jerry would have bumped it a little bit, just a little bit, not too much, not too conservative. But I would say, Jerry, why are you bumping my design, right? And here I am, right out of college. I got a master's degree. I got the computer going. I got the finite elements. I got the daisy wheel printer. We're sharing one computer with 30 engineers in 1988. And he says, Jim, there's unknown unknowns. There are things that are going to happen. You've designed it to be strong enough, but have you designed it to be serviceable? And I never forgot that, right? And this is the kind of thing where you might consider combinations of rebar and fibers and GFRP and silica, fume, or fly ash, or what have you, to get to the best answer. And that could be for a long-term owner. We're also seeing cases where an owner is only wanting a short-term solution these days. Remember adaptability, we talked about that? That it's possible that somebody is willing to accept something that is only serviceable for 10 years, so long as we get that in writing, right? Right, the cost is a big deal. And here again, in my opinion, the thickness design should take only an hour compared with everything else that we talked about. I'm going to stop there.